Hello, my name is Xinyi Ding. The topic I will talk today is about the interpretability of deep learning-based models for knowledge tracing. Most of this work was done when I was in SMU. There are mainly two updates from our previous work. First, we use a much larger dataset at net. Second, we add new discussions about dynamic key value memory network. We have seen empirical success of deep learning in fields like machine translation, object recognition, etc. But most of the time we use these models as black boxes. This is especially true in the learning science community. But the problem is, can we trust these black boxes? We aim to open the box of these models and provide a better understanding of the inner workings of these models. But first, let's review some basic concepts. Recurrent neural network. Recurrent neural network differs from feed-forward neural network by taking the current input as well as the previous hidden states. There are various kinds of recurrent neural networks. On the top, we have the simplest recurrent neural network, and on the bottom, this is a long short-term memory or LSTM. There are three gates in the LSTM: the input gate, forget gate, and output gate. These three gates control what kind of information can be stored and what the output should be. Usually, LSTM performs better than the simple recurrent neural network. Deep knowledge tracing uses recurrent neural network, and the input to this model is one-hot encoding of skill ID and correctness. The output is a vector of probabilities, which corresponds to the mastery level of each skill. In this work, we mainly use visualization to demonstrate our methodologies, and we use TSNE for dimensionality reduction. We concatenate the 6 intermediate outputs from LSTM to form what we call activation vector. In this figure, we plot the first two components of the TSNE of the activation vector for first-time step inputs. Numbers are skill IDs, and we use blue for correct inputs, orange for incorrect inputs. As we can see, this model is more sensitive to the correctness rather than the skill IDs. This figure plots the prediction vector change with time. The x-axis is the skills, and the y-axis is the inputs. We can read this figure from bottom to the top. Most of the time, when you have correct inputs, these values increase by some margin, and when you have incorrect input, these values decrease by some margin. You can also observe from step 14 to 19, this student continuously tries these questions associated with skill ID 113, and the value change becomes smaller and smaller as some indication of convergence. This result is from the this figure is from the system and dataset, and we observe the same results from the AIEd dataset. To further analyze the behaviors of the deep knowledge tracing model, we created a synthetic dataset in which we only have one student, and this one student will always answer all the questions correctly. In this figure on the left, we plot the activation vector change for 100 continuous correctness of randomly picked 3 skills. As you can see, they start at different places in space, but it seems they all converge to the same spot in space. On the right, we plot the activation vector difference among these 3 skills. After 20 steps, the difference is very close to 0. Here is a prediction vector for these 3 skills at step 20. We can see most of these values are above 0.5. It seems this deep knowledge tracing model is not really tracking the mastery level of each skill. Instead, it is more likely learning an oracle state, and when you are in this oracle state, you can always answer all the questions correctly. It does not matter which practice skill you use to get into this state. Deep knowledge tracing model, like any other recurrent architecture-based models, is more likely to be impacted by recent inputs. Consider these 2 scenarios. The only difference is the relative order of different skills. The orders of attempts within the same skill is the same. So for scenario 1, this model is more likely to predict an incorrect response for skill 24 because it follows 3 failure attempts. And for scenario 2, this model is more likely to predict a correct response because it follows 3 successful attempts. We analyzed this behavior quantitatively in our paper. There are some arguments that neural networks are not really learning meaningful representation. The achieved improved performance is merely because inputs are mapped into very high dimensional space in which data points could be easily separated. We did something similar. We randomly initialized the deep knowledge tracing model. We only train the last linear layer. As you can see from this table, from these 2 tables, the results from the untrained model are very close to those from the fully trained model. Dynamic key value memory network has 2 memories, 1 key memory for encoding skills and 1 value memory for storing the states of responses for corresponding skills. Dynamic key value memory network can automatically learn a reasonable set of hidden skills, and we find the size of the memory does not impact the performance, and it is difficult to interpret the skills discovered by these dynamic key value memory network. They may or may not map to those discovered by human experts. This figure shows the memory change, the current memory value minus the previous memory value for different question inputs. On the left, this is a memory change for compact skill ID 1009, which consists of tag 77. On the right, this is a compact skill ID 1078, which consists of tags 77 and 179. It is difficult to visually explain the relationship between these 2 compact skills. To summarize, most of the conclusions from our previous work stay the same. We also add new discussions about the dynamic key value memory network. Thank you.